I think there's two serious challenges, and they're closely interrelated. The biggest challenge is that, of course, renewables are not dispatchable. You don't know when they're going to be there, when they're going to be not there, and depending on the size of the renewables or the scale of it in terms of its attachment to a given grid, that lack of certainty can create a lot of disruption. And so the very same advantages of having the renewables can be offset by the fact that at some point you've got to make up that deficit when they're not there versus when they are. And so that ties to the second issue, which is the bigger the percentage of renewables that you tie to a given grid, the more, even though you're getting more power out of it, which at the surface sounds great, the fact that it is so volatile can actually cause very serious issues on the grid itself, most specifically frequency stability issues that literally can cause the whole grid to come down if you don't do something about it. We look at the very foundation of where the renewables are tied to, and ultimately we see a technology that's 125 years old called synchronous generators, invented by the real Tesla. And unfortunately, that technology was very well suited for literally since the late 1800s to deal with grids that had relatively stable demands, but not able to deal with power that's surging in and out, and to the point that it can't handle it. So the way we deal with the problem is we start out with changing synchronous generators out of the system and applying, putting in what we call variable speed generators. And that allows a couple things to happen. One thing is that we are able to better offset the load deficits as loads from renewables are coming in and out. We dispatch them, but we make up the differences immediately. But as importantly, because of the volatility of the renewables, we actually put in high quality, stable power coming out. Today, any grid where renewables are beyond 20% of the total load, you can't use them. So operators are either not putting more than that percentage of renewables on their grids if they know about the problem. If they don't know about the problem and they get their penetration too high, they actually curtail the renewables, and even though the wind or solar is there, they can't use it. In some cases, we've seen operators actually put more fossil fuel generation on their grids and then dump the power. So we solve that problem at the root cause, where we allow penetration to go from 0 to 90%. Without any disruptive forces, and from 90 to 100%, we just add a little bit of storage so we can go to engine off operations and have a perfectly stable, predictable grid. I think the idea of distributed generation being solar and wind and, say, storage is frankly, I think, not scalable. And I think it's not scalable because it lacks the ability to be cost competitive, and it lacks power certainty, and it also lacks what we would call frequency control to be scalable. But I think the combination of distributed generation with large generation, but distributed generation in a way that's scalable, is the way that's going to happen. And where Innovus plays is we believe we make that scalability happen, because at the distributed level, if you now combine wind and solar with a dispatchable power source, which now gives you power certainty, gives you high quality power that you can actually scale, and yet at the same time dispatch the lowest cost power at any given moment in time, which could be solar or wind, that now truly gives us a truly not just a high performing grid, but also a very economic grid. So I see a very, very bright future if we just have the right pieces.